Today we'll look at hydrostatic pressure, which is basically a static pressure when the fluid is at rest. Now suppose we have a fluid in a container that's closed off to the atmosphere. Okay, so this here is our fluid. And let's suppose I take a free body. So I'm going to take this portion of the fluid and I want to look at the force that's being exerted by this mass of fluid on the one below it. Well, in 3 dimensions, if we take this body of fluid here, so it's going to be like a block. And similarly, we have this lower mass of fluid as such. Okay, so this upper volume of liquid is going to exert a force on this lower volume of liquid. Okay, so that would be the force of the liquid is equal to the density by the volume, which gives us the mass of this liquid here, and multiplied by gravity gives us the force. So this can be written as the density by the area. So this area here multiplied by the height of the column of liquid from the surface is another way we can write the volume. So this here is the perpendicular area. Multiplied by height gives us the volume, then we multiply by gravity. Now if we want to find the pressure, well, what we do is simply divide the force, which is acting perpendicular to that surface. So rho times the area by height times gravity, and we divide that by the area, and that gives us the pressure. Okay, so the areas cancel, and therefore the pressure of the liquid, which I'll write over here, at some height below the surface of the fluid, is the density by the gravity by the height. So as we can see, the pressure of the liquid is proportional to the density of the liquid, and it's also proportional to the height below the surface. Okay, so this here is termed the hydrostatic pressure. And the consequence of the pressure of the liquid only depending on the density of the liquid and the height below the surface is that if we had some weird looking tank, so it looks something like this for example, and we had this filled with some liquid. Okay, so this is all the liquid over here. Well, the pressure at some height below the surface of the liquid is uniform everywhere at that height. So in other words, at these points over here, which are at some height h below the surface of the liquid, the pressure here is all the same. Now suppose that this container is open to the atmosphere. Okay, so if we open it to the atmosphere, so in that case we're going to have a volume of air that's going to be pushing down on this liquid. So we need to add the atmospheric pressure. Okay, so as you can imagine, on Earth you're going to have an atmospheric pressure due to the column of air above the liquid, which extends to the highest altitude on Earth. So above us there's a column of fluid or air pushing down on us basically. So effectively we write the net pressure, the total pressure or the absolute pressure. Okay, so this is the total pressure, is equal to the atmospheric pressure. So this is the pressure that the air is exerting on top of the fluid, plus the gauge pressure. So in other words, what we have is the atmospheric pressure exerted on the top surface of the fluid. So in other words, that would be the force due to the weight of the air on the area over here. And that's the atmospheric pressure. And the gauge pressure is due to the weight of the liquid at some point below the surface of the liquid. Okay, so that's our rho GH. Okay, so what we have is the total pressure is equal to the atmospheric pressure plus the density of the liquid by gravity by the height below the surface of the liquid. And because the pressure is the magnitude of the perpendicular force on the area, basically pressure is a scalar. So it effectively has a magnitude but no direction, whereas the force is a vector which has a magnitude and a direction. And the direction of the force due to the fluid pressure is going to change depending on the orientation of a surface. Okay, so for example, if we look at this container here and it has a liquid in it, and we look at some surface at some height below the liquid, then we have the force due to the pressure of the liquid acts perpendicular to that surface. And if we had a surface oriented at some angle like this, well, that force is going to have the same magnitude but just a different orientation or a different direction, which is perpendicular to that surface. And similarly, if I had a surface that looks something like this, that's further from the surface of the liquid, so the magnitude of force is going to be larger than these two cases because the surface is deeper into the fluid. And if we had another surface like this at a lower point in the fluid, well, the magnitude of that force is going to increase and the orientation is perpendicular to that surface. And I'll see you in the next video.